So I'm running out of time, which is usually the case in every class I teach because I talk too much. But this time, I'm truly running out of time. So I'm at 58th slide, and I think I have like 90 slides or so. And the other slides are also very interesting. And we have 1 hour, so there's no way to do this. Yeah. So what I'll do is I'll cover this part very quickly, maybe for like 5-10 minutes. Skip everything in the middle, which is very good. And then go to the end, which I really like, which is the two-phase liquid-based detonations. Okay. So we saw this picture, how this thing works. What I'm going to say is the one interesting part of it that I want to focus on, which is if I look at this slide here, it already started the movie. We all do, the holy grail for a challenge in combustion modeling is you need to have some physics that's so critical that only as a combustion physicist you can figure it out. Like somebody from the outside cannot come and say, oh, I'm going to do this modeling. But at the same time, that physics should be so dominating that it should control whatever comes out of it. That's the main thing. Okay. Now it turns out for gas turbines, that's not the case. Although we claim that all these flamelets and combustion modeling are important, in the end, it's the large-scale turbulence that controls everything. And the LES guys doing non-reacting turbulence have already figured out everything. We just use the same methods and we simulate other things. So we become like, almost like the machine learning group. Like there are people outside who build machine learning tools, and then we use them and then for our own applications, which is not very satisfying if you ask me. Okay? You have to be in the business of building new things that only you can do. Not you can just take from others and use it. So this problem is interesting because of that. You now have a system where you have injection, fuel and air injection, and you have a detonation that's moving through, a shock wave, which is a highly localized structure. It's very thin. It's only like 10 to 20 angstroms. So we're not talking about, or 10 to 20 mean free paths, right? We're not talking about 1 millimeter or 5 millimeters, not like that. We're talking very, very short distances. So that shock is moving through and it's stirring up. You can think of this almost like a stirrer that goes around and just mixes everything up. Okay? So all your physics is dominated by how you capture the shock moving around and generating turbulence, which the turbulence guys have no equivalent. Okay? The only thing they can come up with is buoyant plumes. If you have helium that is left out, it will create its own turbulence, which is pretty boring. So this is a very complex physics, right? So that's very interesting. It turns out that it's a lot more complicated than this. So you have to inject fuel and air. You have no option about it. That's how you design any kinds of propulsion system. But as you inject this fuel and air, there's a detonation wave that moves over it periodically at very high frequencies. Okay? So when the detonation wave moves over an injector, because the pressure is so high behind it, it just blocks the injector. Now no fuel can come in, or no oxidizer can come in. So for a brief time during that cycle, there is no injection of fuel and air. Okay? And then the wave moves away, pressure goes down, and suddenly everything rushes inside to compensate. So you have this transient mixing process. You block the injector, you inject fuel and air, you block it again, you inject fuel and air. And of course, depending on the strength of the waves, how many waves you have, which direction they go in, all these complexities, that mixing pattern is super complex. Okay? But they are linked. If you don't get the right mixing patterns, you will not get the right detonation wave. And if you don't get the right detonation wave, you will not get the right mixing patterns. So that is a true challenge, right? You have to get both of them correctly. And these are happening over very different time scales also. So it leads to something very complicated. Like for instance, if I look here, this is how, this is a way to look at RDEs. I've not seen this in other places, so I'll tell you what this is. You take that circular object, you slice it, and you open it like a film. You just have it planar. And so the left end of it, 0 degrees, is connected to the right end. So everything goes periodically, okay? You're just looking at it as flat one. And at this point, if you look at it in the top, that's the detonation wave moving along. And in the middle, you have temperature. And you can see it's very complicated. And that complex feature is what is dictating the strength of your detonation wave. And the strength of the detonation wave then tells you how big is your high pressure region, how is it going to decay, things like this. And that controls the bottom one, which is equivalence ratio, how much fuel and air comes through. And if you look at this mixture, it's highly variable. You don't have some nearly uniform equivalence ratio. It goes all the way between 0 in many places to 2, or here it limits at 2, but you'll see that it'll go even up to 3 or 4, right? So it's a very variable mixing process that happens here. So what we have, and I'll skip to that part, is this schematic. And this is at this point only schematic. We do not know how these are all coupled. We can draw this, and I can explain to you all of this stuff, and it will make perfect sense to you. But there is no mathematical description for this. From this, I cannot design it in RDE at all. In fact, right now, this is the challenge. I know that if I have annular geometry and I put in fuel and air, I can somehow get it to be a detonation engine. So it will have a moving detonation wave. But what I cannot predict ahead of time with all the computers in the world and all the lasers that I can have is how many detonation waves will operate for a given operating conditions. What speed will they move with? They will all not move at CJ speeds anymore because it depends on the mixing pattern. So they'll move a little slower than CJ speed, sometimes a lot slower, like only 50% of the speed. I don't know that speed, and I don't know the width of the detonation wave. How large is that high pressure region behind that shock wave? So it leads to this complex pattern. There is some link here, and we do not know what this link is. And so this remains one of those topics where there are experimental groups that will build detonation engines. And in fact, there's a very famous exercise. I was part of this, Purdue was part of this, half the experimental labs in this country were part of this, where a single geometry was taken. It was given to 4 different experimental groups across the country. And they were asked to run a single case, methane and oxygen for a rocket, and to measure what will happen. So the 4 experimental groups initially had different results, but over time they figured out if they do things a particular way, you can get almost identical results. The number of waves, the speed of the waves, what thrust you will get, ISP, everything was very close for different operating conditions. So what we know is that this experiment is reproducible. It's not predictable. I cannot tell you ahead of time how many waves are going to be there, but I can take it to different labs, different people can do it, and they will get the exact same results, even though they do not know the reason, which is very frustrating, right? But then come the computational groups. There's also 6 of them, including my own group, and there are 4 or 5 other groups. We all come up with our fancy softwares, all the detailed chemistry, GPUs, CPUs, whatever we come up with. We all do the simulation, and we get 6 different results. None of them agree, and to this day, this has been 3 years, none of us can make anything agree. The 2 groups do not have the same results, okay? We all use different numerical methods, our geometries, our grids are a little bit different. There are variable properties, right? But there is no other CFD exercise that I know of where experimentalists can come to an agreement and the people doing simulations have no clue why we get what we get. So this to me is a true challenge. Like the one thing if I want to solve before I'm done would be to figure out what is going on here. Like why is it that it's so complicated? There are many other problems, non-equilibrium, quantum mechanics, whatever. Everything you can figure out if you just do things, but this one is somehow escapes it, okay? So that's something to keep in mind. I'll stop with this idea here, but think about it, and I can give you more examples of this later, or I can point you to papers and so on. I want to switch topics. One final topic, yeah? So it's 4:30, so I want to focus on this. This again is very fascinating. This is the as current research course. This is like, there's bleeding edge, and then there's one step ahead of the bleeding edge. That's what this is, okay? So no one burns gas phase fuels for any propulsion applications, okay? So you're not going to take hydrogen in gas form and then think you're going to fly an aircraft, because it does not have the density, the energy density to do that. You have to burn liquid fuels, okay? Even if it's hydrogen, you have to liquefy it to carry it or do something like that. So you need liquid fuels. Now, the problem is already, even with gas phase fuels, this is not a simple problem. Now you have liquid injection into this, and you have to figure out what will this liquid do to all these detonation processes. Now this is a big conundrum. There are certain things that are very frustrating because you do not have a handle to, or you do not know where to pry open, right? A research problem. This is one of them. So I show you this problem. Like, you don't even need to look at the RD for the moment. We'll have this problem where these are the best images we can find from Kareem Ahmed, is one of the leading experimentalists on this topic. That's a single droplet is being hit by a shark, okay? Shark-droplet interaction, very popular problem for computational physicists. It really tests all your coding skills and algorithmic skills. So he has done experiments of this, and he has these kinds of measurements. A shark hitting a droplet, okay? Now, what we know from looking at droplet evaporation theory, which Professor Matlon will cover tomorrow, I think, or Friday or something like this. Droplet evaporation theory is that there is a particular rate at which droplets will evaporate. And you can control it at some level by heating the droplet, things like this. But there is a rate. It doesn't, if you suddenly expose the droplet to a high temperature, it doesn't mean it immediately says, I evaporate. It's not like that. It still is a finite time, okay? That time matters. So we'll come to that repeatedly. What we're interested is in knowing how much time it takes for a droplet in liquid phase to go to gas phase, mix with oxidizer, and react. And can all of this happen after the detonation wave passes over the droplet, but before that Mach 1 choke point arrives? Because if it happens after it, it's of no use to the detonation wave, okay? This is something we are not able to figure out. I'll go through what is the logic of this. So think of this problem first. I'll tell you what else is going on and why we care about it. So this is in multiple parts. I'm going to run through this so that you see what's happening. Same problem as before. We're going to inject fuel and air into the system. That's how we can run these RDEs. And if you think about the problem, there are many, many different things in this. So the fuel is coming in as a liquid jet. It has to interact with the gas jet, break down, which is called atomization. And once it atomizes, there is this population of droplets that are there. If you wait too long, those droplets will fall down. Now gravity matters, yeah? So it will fall down, or they will go hit the wall and start, pooling up on the wall. So you don't want that. So you want these droplets to atomize and just be there while the detonation wave comes through, right? So which is a design problem already. And then the detonation passes over these droplets, and it has to somehow use them effectively. Now, we have done simulations of this, and I'll show you what our simulations are. This is very primitive. This is one of the first full-scale RDE simulations with liquids. And so we use the same geometry I talked about, the 6 experimentalists, 6 computation people. Same geometry. Instead of methane and oxygen, we now inject liquid RP2 into it, like rocket propellant grade 2. And an oxidizer is oxygen, so it's like a rocket, so it comes through. So these are the configuration. So there are 72 pairs of fuel and oxidizer injectors around the circumference. And so this is the faceplate between the inner cylinder and the outer cylinder. And then now a detonation wave is going to pass through. So I'm going to show you how this thing works. Nothing very remarkable, okay? So we did these calculations. You see those green things coming through? Those are the droplets. And we just inject droplets. We forego atomization because it's too complicated. So we assume droplets of some size are coming through. We inject it. We do the detonation calculations. And this is what we get. there are 3 waves, if I remember this correctly or calculated correctly, the 3 waves that are moving around, and that's the heat release rate. If you look at one section, it will look like this. So those are the fuel and air coming in. You can see that, and there's a detonation wave passing through. Okay. Now the problem is that wave moves at 1400 meter per second. The CJ speed for this is much higher. I don't remember exactly what the number is, but it could be like 2000 meter per second or something. So the 0D analysis will tell you RP2 O2 gas mixture will travel at 2000 or so meter per second. You get only 1400 meter per second, which is very low. So it's not doing what it's supposed to do. It's going very slowly, okay? But this is a simulation we could do. And we try to track different quantities, whatever, and so on. There is a single assumption we have made in this, and that's the root cause for what I want to talk about now. So we have assumed when these droplets get hit by the shock wave, nothing happens to the droplets. They just react as if some shock has passed by, so the induced velocity moves them differently, but nothing else, no change to their immediate state. The surrounding gas is now hotter, so it's going to start evaporating faster. But what you will see is that evaporation rate, what is called D squared law, is not very fast. In fact, it will take about half of the cycle time, half of the time for the wave to go around the circle before these droplets will fully evaporate, which is too long. That shock wave is spanning about 5 degrees. That's the detonation wave structure out of 360 degrees, okay? And I'm telling you that these droplets take 180 degrees of the shock wave before they will evaporate, which means they are not within this detonation structure at all. They are, the high temperature is making them evaporate, but they are not the ones driving this whole shock structure, which is very confounding. This is not what we would expect. So I have this theory that there are 2 ways an RDE can work in liquid fuel systems. So I call one of them the coupled detonation mode, the other the decoupled detonation mode. So the decoupled is the easier to see, so I'll explain that first. It's based on what we saw in the previous simulation. There is a shock wave. It goes through the droplet. Maybe it breaks them into smaller droplets. Maybe it doesn't. That's not relevant at all. But it takes so much time for the fuel to evaporate and mix with the gas around it. No appreciable heat release can happen before the choke point behind the detonation wave comes through. So the wave passes by. The droplets are now cooking. They will evaporate at some point. They'll mix and react, but not in time for this shock to process it. So what happens is that this shock passes by, it processes these droplets, it prepares them. They evaporate, they mix, and now they're ready. And then the next detonation wave comes through, and that's the one that really consumes this gas phase fuel air mixture. So in reality, this 2-phase RD is operating like a single-phase RD. The first shock wave is evaporating the droplets, and the second wave is now consuming the evaporated fuel air mixture, okay? So that's what I call the decoupled detonation, and we can do some math on this and show that this will actually lead to wave speeds that are much lower, things like this. So you can do all of that analysis. But that's not interesting. That's not a useful way to operate this. It's very inefficient. What you really want is this coupled detonation mode, where you have these droplets, the detonation passes over, and some magical physics happens, okay? That it immediately evaporates. And when I say immediate, don't think like, nanosecond. Think more like half a microsecond or 1 microsecond, something like this, okay? Which is still appreciable time. It's not negligible time. It evaporates, it mixes, and then it starts burning before the choke point. I also allow a little variation. I assume that in a liquid phase detonation, maybe the detonation wave is a little thicker. It doesn't have to be very thin. Maybe it spans like 4 or 5 millimeters, not just 1 millimeter like it does in gas phase. It's possible, okay? So I make that assumption. I want to know if that's possible, okay? And when we did those calculations, this was for a project many years ago. And then at the end of the project, my conclusion was, no, this will not work. It's going to be like this, okay? And then it was done. We wrote a report, and that was the end. The student graduated. Everything was perfect. And then we had this additional study that University of Central Florida, where Kareem Ahmed is, he conducted this. And it really triggered a whole different set of problems. So I really hope that he did not do this. So this is his experiment. We decided doing that RDE is just too complicated. You cannot measure anything inside it. You're just making approximations and hypotheses that you cannot test. So he simplified the problem, and he said he's going to have a tube filled with, I think, hydrogen and oxygen. You should never do this anywhere, okay? That is I mean, there are pipe bombs, and then there are pipe bombs. This is one of them, okay? So he fills with hydrogen and oxygen. I cannot imagine a graduate student agreed to do this stuff, but he does it. They're of course safe about it. I'm just making a joke. It's not that they're unsafe about it. So they mix it, but he has in the middle a pair of injectors, RP2 and O2, right, that comes through. And then they are in the middle. So what he does is he initiates a detonation wave ahead of this. The detonation wave is now consuming hydrogen-oxygen mixture, so it's moving really fast towards this single pair of injectors that's injecting liquid fuel and oxidizer, and it hits it, and it moves past it, okay? So what they measure is the wave velocity, the rate at which the detonation wave is moving as it goes through this mixture. And what he finds is that initially, the hydrogen-oxygen mixture, there is a particular detonation velocity, which is very close to CJ speed. So they're able to confirm that it's the CJ detonation that's happening in that mixture. It passes over the RP2O2 mixture. Now the heat release rate increases because there's new fuel. And as it goes through, it accelerates. So it starts becoming faster. So which tells me that all of that heat release has happened within the detonation wave. So for the first time, we now have an experiment where you could send a detonation wave, it passes over the liquid fuel injectors and actually speeds up, okay? So one of the explanations could be that something happened there that allowed that RP2O2 mixture to immediately burn, the liquid RP2 to somehow transform and immediately burn to support that detonation wave, okay? But this is the extent of this study. Like, they had different things, but you know, this is the most of what they could come up with at that time. So this ended there. Now, we thought we will do the same calculation with our code, the same thing that we did with the RDE stuff, right? So the same models and everything. And so we do the same. So there's a movie here, which is not critical. But what we find, the plots are not very convincing here because it's too jagged. No difference. Our speed stays roughly the same. Because we already know our evaporation models are so slow that it's not going to release the heat behind the detonation wave. So the simulation is completely fair. Okay? They don't predict at all what's going on here. So this was it. This was at that point. So there's a transition, and then we are done with it. And then comes these calculations and these pictures. So the picture on the bottom right is from James Arthur Nichols, who was a professor at Michigan. And he did these experiments in the 1960s. And he was doing the same. He was interested in detonation engines. In fact, he was one of the founding fathers of partial pulse detonation engines, PDEs. And he came up with these experiments where he would suspend droplets, send a shock wave or a detonation wave through, and see what happens to them. And the time scale he was observing was vastly shorter than what we would have got from simple evaporation using d squared law. It just did not fit, okay? So we started looking at it in more detail. So simultaneously, this group at Stanford also started working on the same topic. So we have a joint project. It's all one big project. And Nick Kateris, who will soon be a professor at Imperial, he did these calculations. So we cannot do really continuum simulations of this because there are a lot of things we don't know. So what Nick did was to use molecular dynamics. And so when you do molecular dynamics, you have to make some approximations, which is not very important here, but let's say that's what he used. And those conditions are given. So there's a droplet there. I'm going to run a movie, and then you will see that there's a shock wave, which is a different colored droplets, molecules will come hit this droplet, and then you'll see this droplet changing as it goes along. Those pictures are at the bottom as they go through time, so that those are all in PS, which is picoseconds, right, as it goes through. Because it's molecular dynamics, everything is very small. The droplet itself is, if you look at the calculation, is 20 nanometers. So no droplet can be 20 nanometers. But this is for the molecular dynamics calculation. So if I run this, you see that green fluid coming through, and it takes the droplet and it shatters it. Okay? And you can see that that picture is similar to his last picture, Nichols' last picture. So behind the droplet, there is a region where there's some kind of fluid that's dense and it's coming out of the droplet. So this is the extent of the simulations. But what they concluded from this analysis is that when a shock hits a droplet, it's not the shock that matters. That passes very fast. The fluid behind the shock, which is called the induced flow, because every time a shock moves, it's dragging flow with it, which is why when you see explosions and you see videos, you see this palm trees tilting, right? So that's from the induced flow that the shock takes, not the shock itself. So that induced flow now, which is very high speed also, is now hitting these droplets, and they are heating up these droplets, the interface molecule. So they're transferring energy into this droplet, heating it up at much faster rate than what you will find from d squared evaporation loss. So this is their hypothesis. And if you do this, they found that you can have evaporation that's much faster than d squared law. And it's to the point that you could potentially support a coupled detonation. Okay? This is the theory. It was not fully convincing to me. It's a convincing argument, but it's not fully convincing to me. So we took this. I'll skip these in the interest of time. And we did continuum calculations. And I'll run this a couple of times to get a hang of it. So there's a single droplet sitting in the middle. We have special solvers for this, nothing to do with anything I described before. These are liquid simulations using what is called a diffuse interface method. So it's a two-phase continuum description. You hit the droplet with different Mach number flows. That's MS is the shock Mach number, so it's Mach 2 or Mach 3. Okay? So you hit these droplets. And when you hit the droplets, there are things that happen which is very interesting to see. So if I go back, so as the shock hits, the flow behind it now compresses the liquid, it pancakes it. There are small droplets that are shed from the outside. These are the tiny droplets. And then the core of the big droplet tries to expand out, and the whole thing shatters at some point and generates very tiny droplets. Okay? And you can come up with a time scale which was proposed by Ranger and Nichols. So all of this is plotted in that time scale. So the tau is 0.4 or whatever that counter that's running is in this non-dimensional time. And what we find is that all of this shattering happens very quickly. So going from, typically in these combustors, you will generate droplets that are like 20, 30 microns. This is the typical size of the droplets. You can take this 20, 30 micron droplets, hit it with a Mach 3 shock like this, and suddenly those droplets become very small. They shatter very quickly, and they become not 20 micron, they become more like 3, 2, or 4 micron droplets. Okay? Now, what happens is evaporation is proportional to surface area. Okay? If you make very tiny droplets for the same mass, now you increase the surface area dramatically for the same mass. per unit mass. Each droplet has a smaller surface area than original, but together for the same mass, they have many times higher surface area. So they start evaporating very quickly. So motivated by what Nick did with the MD calculations, if you do even continuum calculations in a slightly different way, you come up with the same result. That when the shock hits the droplet, there is a sudden change in how the droplet behaves, and it shatters in a very short time. And as it shatters, it distributes itself widely. So initially the droplet is sitting in 20 micron space. It goes and it shatters itself in about a millimeter box that you distribute it. So the shock not only affects the evaporation time, it also distributes the fuel air mass behind it. So now at those locations, evaporation can be much faster. Now there is hope that there could be evaporation. Now I say this in a way as if I figured out all of this, but there are a lot of assumptions made in each one of these, the molecular dynamics, the experiments, and the simulations. So we get results that are similar to one another. I don't know if it's similar because we have all seen each other's results, right? So it's like students doing an exam, right? So all the results look the same, open book exams. Or truly there is a process here that leads to the same evaporation time scale, okay? Now the part that Nick and Wang figured out, which I think is important, and I'll go back to this, is this idea that when you have these molecules in the gas phase which are coming at very high velocities, they impact that pancake droplet, which is the one in the middle. If they impact it, the energy transfer can be significantly faster. So instead of having a conduction-based energy transfer that depends on the static temperature of the droplet and the static temperature of the gas, you might have an energy transfer that's based on the stagnation temperature of the flow and the static temperature of the droplets. And at high-speed flows, the stagnation temperature is very high, right? So the rate of energy transfer can significantly increase. So if you do this, you will have a very high evaporation rate. So it's possible that something like this happens. Since then, Karim has done many more experiments where this seems more plausible. We still do not have full confirmation that this is how it seems to work, but we're beginning to understand that in a shock-containing flow, droplet transfer from liquid to gas phase may not happen the way typical evaporation happens. So tomorrow, when you go through the evaporation that Professor Matlon teaches, ask him about this. Ask him if he knows about two-phase shock interaction, and then you'll see what he says. Yeah. Okay. That's all I had, actually. So I skipped many in the middle, and I got to the end very fast. Hold on. Is this about this?
Yeah.
Oh, okay, ask me, yeah.
So you mentioned that you had considered this continuum hypothesis where this bubble is getting, droplets is getting pancake, and you see a spread of smaller size droplets. Mm-hmm. So actually when you explained me, like you were explaining that graph when you did not note, like where the speed did not increase as was expected from the experiments, I was initially thinking of this that the droplets cannot stay the same size when it's getting hit. But so I would have thought like initially doing it like to impose a Gaussian distribution or something to try out that let's say by assuming that the droplet diameters, if like Ahmed you showed some of his experiments, the initial experiment, like did he measure the droplets, kind of the size of the droplets, if any way it's possible?
Yeah.
Then I would have just taken that and then with the Gaussian distribution.
This is exactly what we did. So he initially did only the impinging study, no detonation wave, and he gave us a size distribution, a Sauter mean diameter and a distribution, log normal distribution. So we imposed it in our injection for the droplets. We did not do atomization for that particular case, right? And so we use a log normal distribution and with the prescribed Sauter mean diameter. And this is what we get. The issue is not the initial atomization when the liquid fuel and the oxidizer interact. right? The issue is the post-shock droplets, and there's no way to measure that. So when the shock hits the droplet, even the initially atomized droplets will undergo a secondary atomization now.
That's when I would want to put another Gaussian distribution, not before. So I was just talking about that, like because of course after the atomization, when the fuel is entering and when the shock wave has passed with, I cannot imagine the droplet to be staying there the same. It should be coarser, like more finer and more finer. Like it should be very fine so that just within a snap it will just vaporize. Because I think the diameter, the d square law, it can stand, but it's again dependent on the diameter. So the critical can be what is the diameter that we are considering? Is it actually the diameter that can be captured? Like what is the finest level of diameter that it's going, and then maybe it won't be perfect, but we can try.
So this is what we know. If I make the assumption that droplets instantaneously evaporate, like within 1 delta T of the CFD solver, right? I know that I'll get a detonation wave. So we have confirmed it. If we use d squared law, I know that we won't get a detonation wave. That also we have confirmed. So clearly I can play a game where I slowly vary this evaporation time and see what gives me the right result. But that is not the way to do a simulation, right? There has to be an external evidence to what you prescribe. The two limits are obvious to us. We do not know what's the correct distribution. And there's no way to measure it because you cannot measure in the distance, right? So the best that can be done is that you take a single droplet of some size and you try to hit it with a shock and try to measure something. Even there, I think measuring droplet sizes is impossible. The best you can do is like the shape and the location, the size it occupies, things of that nature. Yeah, there are no measurements, yeah.
And is it possible to couple your continuum, like the simulations for this continuum thing that you showed with like that same thing after the shockwave is hitting your simulation, like just to couple these two simulations, because that looked kind of what I would expect after hitting it. So just coupling that part somehow, or maybe deriving some kind of conclusions from one of your simulations and then using it for the other simulation. That would kind of provide some.
Yeah, that's good. I think that's the right path to take, right? The problem is each one of the simulations drains all the computing power that we have. So that's the issue. So we have to wait for the next allocation of supercomputing time before we can do anything. But you're right. I think the way I would think about it is that you do shock droplet interaction for different Mach numbers, try to extract some correlation for the diameter distribution, and use that in the full-scale simulations. Yeah, this is the goal. That's right. Any other questions for this particular thing?
What solid particles like soot, for example? Do you have any experience with that, or how would you approach that in contrast to liquid particles, I guess?
Soot particles for what?
In the exhaust, when they're part of the exhaust, how do they behave, I guess, when they get hit with detonation? What's your take on that?
What are you talking about? You're saying...
So in the exhaust, when there's soot particles, there's still, I guess, oxidizer left, or air, or oxygen, and it's still hot enough for it to burn. How do you...
Oh, okay. Okay. You somehow have to support the detonations, right? Are you assuming that the soot particles oxidation will provide you enough energy to...
Maybe, or maybe they're a byproduct of the combustion.
They could be. If they're byproduct of the combustion, solid particles will not break the same way as liquid droplets. So they're going to be weaker in general. So they're not going to break down as easily. I'm not sure about their oxidation. Those timescales still depend on what's coated on the droplets. Sorry, on the soot particles. I'm not sure about that. Well, not if it's soot, right? It depends on where you form the soot. No, you can have hydrocarbons or other species coating on it. They could be, this is all the soot study. So that's why there are different size soot particles. You can have hydrogen sites on top. So there are additional, and they're also not a single particle. There's a structure to it. So they can break down or they can react first. So there are other complications, but I'm not sure. I have not thought about it. And when you say this, all I know is that all these guys, Nichols and everybody, in the early 60s, they studied this problem, then the liquid problem, and then they studied how to clean sewage pipes using detonations, and which is similar to the problem that you're raising. Because if you want to pass detonation over a surface, and it's going to cleave anything that sticks to the surface and then carry it out. Maybe that's what it will do, but not a rotating one. Yeah.
How do you couple shelf droplet interactions with other processes like flash boiling, for example? That adds an added layer of complexity.
Yeah, I don't know. I have to say I don't know. So flash boiling, you can have models for it, but they're not. So the whole droplet may not undergo flash boiling. It's possible that only a part of it that exposed to the right conditions undergoes flash boiling, right? So that is much more difficult. You also have this thing forming a pancake and like a cup-like structure. At the back, the pressure drops, so you can have cavitation. So that can also lead to other problems. So that we do not know. That's a much harder problem, yeah.
Can you speak to if, using a liquid fuel and a liquid oxidizer, because combustion inherently happens in the gas phase, does that reduce contact burning at all?
Yeah, I think contact burning is much less when you have liquids, that's for sure. I think the bigger issue is that if you don't tune the injectors well, you will coat the walls with liquid, and they will slowly burn. When you think of contact burning, it's at the top of the interface between the detonation wave and the injector. This is more the wall and the passing hot gases. That might be a bigger. So you'll start coating the walls with soot, and after a minute of operation, you just have black surfaces, right? So that's what might happen, but not the liquid itself.
I wanted a question about where you had the continuous simulation. I think on slide 84, where some structures were forming that looked very very quadratic, and maybe this is very stupid, but is that somewhat related to this time scale or to a frequency? Because it looks a lot like if you expose particles to a certain frequency and they form structures, and I was wondering why there was this rectangle or
in the liquid simulation. Oh, you mean in the shock droplet? That's a plotting artifact. There should be no squares don't form in fluids, right? It's not it's very rare. It's a plotting artifact. So if you refine the mesh around it, you will see that they're actually more circular, but they look like it. But there are dominant frequencies. You have, what's forming these are Rayleigh-Taylor instabilities, and so there are frequencies and modes that they have. So if you have droplets that are twice the size, they will behave very differently from droplets of a particular diameter because the frequencies do different things. Yeah, certainly. Yeah. No other questions? Okay. All right. So this is mostly what I had. I don't know if I put this for the entire thing or just for this, but I think it's for the entire thing. And so I was trying to think what I should teach, and it was not clear to me. I asked some of my students, and I told them not to come to the classes, but they still come here. So I just put in things that they have not seen me talk in general. So that's my whole slide deck, except for the last one, which, by the way, many of them did the research that goes into this slide deck, right? The one thing I want to say, and I think this is important, we had a lot of questions today about what we should work on or what is uncertain, things like this. I think what has helped me is to not stay static. Do not assume that what we are doing today will happen tomorrow or a few years from now. So trying to bring different ideas into the field sets you apart, and then that gives you like a net worth that you can expend when times are lean, right? So I see already in talking to many of you that you think very differently from how I would think about these problems. So I really encourage you to keep looking at it that way, yeah? And maybe all the things I talk about today, like detonation engines or things like that, next time, maybe it doesn't matter at all. They're all gone. It's possible, yeah. But this is all I had to say. Thank you so much for listening, and of course, send me emails if you have any questions about whatever I discuss or covered here, sorry. Yeah, thank you.